So let's start continuing what we were explaining in the last session about the rate of the reactions. So we said that the rate reaction law is what can be found experimentally only. For example, if you have a reaction where the rate of the reaction is equal to K multiplied by the concentration of the first reactant, let's say it's B, multiplied by the concentration of the second reaction, which is B, and this one to the power of n and to the power of m, where n and m are the rate of the reactions. So rate of the reaction power, and this one can be found only experimentally. We said that they can be found only experimentally, and they have no relationship at all to the stoichiometry or the coefficient of the numbers. And to prove this one, we can see from one table here that this is correct. For example, these reactions, the first reaction is H2 reacts with I2. The rate of the reaction is equal to the rate constant multiplied by the concentration of H2 and multiplied by the concentration of I2, everyone to the power of 1. So this is by chance, here is 1 and 1, and the concentrations are 1 and 1. If you are thinking that it is related, let's have a look at the second equation, where NO gives and CO give us O2. Here, the rate of the reaction is equal to the concentration of, I'm saying here K, and it should be rate. It should be the rate of the reaction, not the K. We are saying rate of the reaction is equal to K, and here the rate is equal to K multiplied by only the concentration of NO to the power of 2. So it's not related at all to the concentration of CO, and the number of moles of NO is 1. So don't think that this is related, because here it is showing 2. So if it is related to the coefficient, it should have been 1, but it is 2 here. And again, the rate of the third reaction is equal to K multiplied by the concentration of H2, which is to the power of 1 here, not 2 like the coefficient, and NO to the power of 2. And here the rate is equal to the concentration of K, or the K multiplied by the concentration of BrO3 minus, multiplied by the concentration of Br minus and H plus. So it's all not related, and you can see that it's not related at all. Just a review of how we are finding the rate of the reaction experimentally. For example, in the equation that we mentioned here, that's 2H2 plus 2NO gives us 2H2O and N2, and these are all gases, by the way. In order to find the rate of the reaction, you have to do a series of experiments in which you are fixing the concentration of one of the reactants first. Let's see how the concentration of H2 affects the rate of the reaction. So let's see how the rate is related to the K and the concentration of H2 by fixing the concentration of NO, making it constant, and varying only the concentration of H2. When we vary the concentration of H2 and fix NO, we will find that the reaction is to the power of 1, which means that every time I double the concentration of H2, the rate of the reaction will double. If I treble the concentration of H2, the rate of the reaction will treble, and so on. And to find the relationship between the rate of the reaction and the concentration of NO, you have to vary this time NO and make the H2 fixed. So when you do that, you will find that the reaction is proportional to the concentrations changes in NO pi to the power of 2. So when the rate of the reaction, when the concentration of NO is double, the rate of the reaction also will be quadrupled. So if you multiply it by 1, it will be multiplied by 2 for the rate, and if it's multiplied by 2 here to the power of 2, so it is, the rate will be to the power of 4. When you find the rate law for H2 and NO, you can combine them. You can combine them to find your total rate law equation. We will find K multiplied H2 to the power of 1 multiplied NO to the power of 2, and as in chemistry, we usually don't write the number 1. We'll try to practice this one by finding the answer to these equations. Write the rate equation for each of the following reactions. Cyclopropane changes into propene, where rate is proportional to the concentration of cyclopropane only. So you want to say that the rate is equal to K multiplied by the concentration of cyclopropane only. And P, rate is proportional to the square of the hydrogen iodide concentration. So rate is equal to K and the concentration of hydrogen iodide only to the power of 2. And third one, the rate is proportional to the concentration of C12H22O11 and to the concentration of H plus ions, both of them. In the fourth one, rate is proportional to the concentration of HgCl2 and to the square of the concentration of K2C2O4, so squared. And the last one, the rate is proportional to the concentration of CH3COCH3 and the concentration of H plus ions, but it is having no effect, the concentration, changing the concentration of I2 has no effect, so we will not mention it in the equation. In summary, we can say that the order of the reaction with respect to a particular reactant is the power to which the concentration of that reactant is raised in the rate equation. For example, a rate equation involving only one particular reactant, the order is the power of the concentration showing in the rate equation. So let's say when you are writing about order of reaction, you must distinguish carefully between the order with respect to a particular reactant and the overall order of the reaction. What is the overall order of the reaction? How can you find it? If you have an example here, that the rate, for example, is equal to K multiplied by the concentration of H2 to the power of 1 and NO2 to the power of 2, the order of the reaction with respect to H2 is 1. And the order of the reaction with respect to NO2 is 2. But what is the total order? What is the overall order of the reaction? The overall order of the reaction, you can just find it by adding the two orders. So 1 plus 2 is equal to 3. So overall order is third order. So it is third order overall by adding the two. Some reaction orders actually are fractions. So for a reaction CH3CHO gas to give us the methane gas and carbon monoxide gas, this is a strange reaction because the order of this reaction actually has an overall order of 1.5, where the rate of the reaction is equal to K multiplied by only the concentration of CH3CHO, and this one is to the power of 1.5. Special reactions having free radicals have fractional order of the reaction. Another important point that we discussed is the units of K. The unit of K varies a lot according to the form of the rate of the equation. Because where do you find the K from? If you said that the rate of the reaction is equal to K multiplied by one reactant, so to find K, it's equal to the units of the rate divided by the units of A. What is the units of the rate? Rate of reaction is the speed of the reaction, how the changes in the concentration. So it is mole per liter or decimeter cube divided by second. And the concentrations of A is mole per liter again. So when you cancel these two out, the unit of the rate constant, which is K, is only gonna be S minus 1. While if it is a reaction that depends on two reactants, like it's A and B, or it's A squared or B squared, every time you are going to get different units. So you have to find what is the rate low, and then accordingly you can find your unit. Let's try to find the unit here. it will be equivalent to rate. What's rate? Unit is mole divided by liters and seconds. And the one is repeated twice because mole per liter for A and mole per liter for B. So when you cancel this liter with this liter, mole with mole, your unit will be S minus liter, S minus 1, and mole minus 1. So every time you have to find your rate law so you can find the units of your K. Okay, how can we identify the order of the reaction? We can identify the order of the reaction in three main ways practically. Either we plot a graph of the reaction rate against the concentration of the reactant. So if you make a graph here, if you make a graph here and put this graph between these two, the rate of the reaction versus the concentration of the reactant. What is the concentration of the reactant now, and what is the reaction rate? Another method of doing that is putting a graph between two different things. The concentration of the reactant against time. So I'll see what is the concentration here of my reactant and what's time. And the last method is by making a curve x again against y, where x is still time, but here still time, but y will be a different half-lives, and we'll see what is the different half-lives of the concentration. So different half-lives versus time, and let's see every one of these separate. First, the graph of the reaction against the concentration. So we'll see first the graph of the reaction, and we define the order of the reaction by finding the rate, the constant, the reaction rate against the concentration of the reactant. In practice, we are finding the rate of the reaction many times its order by just looking at the curve of the reaction. You can just find the order by just looking. So a graph of reaction against the rate of the reaction, this is the rate of the reaction against the concentration, will tell us whether a reaction is zero order, first order, or second order, or third order in respect to a particular reagent or overall. It's very rare to obtain an order with respect to a particular agent more than the second. So usually if I'm talking about a certain reagent, like my rate in respect to a certain agent, usually I get it either 0 or 1 or 2. I'll see in this graph that the shape of the graphs expected for different order of the reaction. So if I made the rate of the reaction here and make it versus concentration and see that the curve looks like that, it's a straight line like that, then this is a zero order reaction in respect to this reaction. So I'll say the rate of the reaction is equal to K. And when you are speaking by K, there is no concentration of first or second reaction. So both of them, the order is 0, which means that varying their concentration does not affect the rate. Again, if I make A to the power of 0 or P to the power of 0 as the reactants, it means they are not there. So I have canceled them out. So the varying the concentration of them does not affect the rate of the reaction. So rate is equal to K only. What if it is a second order reaction or first order reaction? If it is first order reaction, then making again the rate this time of the reaction versus the concentration of this reactant will give me a curve that it is straight line. So the curve will be a linear like that. So this means that this is a first order. First order means that the rate is dependent only on one reactant. So rate is equal to K multiplied by only one reactant. Let's say it is A. And the other one doesn't have an effect, because if the other one is there, it will be at least 1 and 1, so it is 2. So it's second order as total. So it can be only dependent on one of the reactants to the power of 1 only. What about the second order reaction? In this case, if you make a curve between, in this case, if you make the curve between the rate of the reaction again and the concentration of the reactant, you will find that the curve looks like that. The curve will looking like that. And as we said here, this is called the second order. the rate of the reaction is dependent on K and A to the power of 2. So the total order of the reaction, is 2. Here it is total 1, and here is total 0. But what does this mean, and how we can make use of it? An example of a zero-order reaction is the reaction where the ammonia changes into nitrogen and hydrogen. The rate equation here, when we find it experimentally, is equal to K multiplied by NH3 to the power of 0. So there is no effect at all of changing the concentration of NH3 on the rate of the reaction. And any number to the power of 0 is equal to 1. Anything to the power of 0 is equal to 1. So you can just remove this one and say that the rate is equal to K. This is what's known as a zero-order reaction. When you make a plot again, like we said now, when you make a plot of the rate of the reaction versus the concentration of the reactant, we'll find that there is no change. What does it mean there is no change? When we see the graph, whatever you change the concentration, so concentration keeps changing because you are changing the x-axis, you see that the number here at the rate is the same. So the rate is the same. Whatever you change the concentration, the rate is fixed and does not change. Well, if you have an example for a first-order reaction, this is a reaction between nitrogen oxide, dinitrogen oxide, to form nitrogen and oxygen. The rate equation, which we get from the experiment this time, let's separate this from each other. The rate of the reaction, which you get from the experiment this time, gives you a different curve and a different reaction. Because the rate here is equal to what? It's equal to K, multiplied by the concentration of dinitrogen oxide to the power of 1, So it depends on the concentration of this reactant to the power of 1. And if you make again, so this means that rate is equal to K N2O. Why? Because this is to the power of 1, and there is no effect of another reactant. In this reaction, actually, there is only one reactant. But if there are two reactants, then it will be only dependent on one of them. So what is the rate? Mister, compared to the concentration? When you change the concentration this time, the rate of the reaction is always going to change in the form of straight line. So it is directly proportional. Whatever you change, the rate of the reaction, the concentration of the reaction, the rate of the reaction is going to change. What about an example of a second-order reaction? This is all relative to one of the reactants only. Like this reaction is between nitrogen dioxide and carbon monoxide. Here I will find that the reaction rate is actually dependent on both or one of them. It's dependent on one of them only, which is K, but to the power of, which is rate constant, K to the power of 2. So NO2 to the power of 2. It's dependent on NO2, and you can write it in another way, but no point of it. That's KNO2 to the power of 2, and CO to the power of 0. So it's zero order, and zero order means that when you add these two together, when you add 2 and 0, you got 0. That's why no point of keeping this one. That's why you cancel it out. Anything to the power of 0 is 1. You just write it as it is. Rate is equal to K to the power K multiplied NO2 concentration to the power of 2. This time, if you make a curve between the concentration and the rate of the reaction, it's gonna look totally different. Like we drew it in the previous paper. Why is that? Because the rate of the reaction will depend on the change in the concentration of this reactant, but it will give you a different shape. It's directly proportional to the square of the concentration of NO2, not directly proportional to the concentration So the curve will somehow look like that. When you concentration of NO2 doubles, the rate of the reaction increases 4 times. So we can see this is the curve looks like that. So for example, if the rate at 1 mole per liter is certain rate, that's one-fold increasing the concentration. So the curve will look like that. Okay. Now instead of seeing the graphs, now instead of plotting the graphs of the rate of the reaction against the concentration to find the order of the reaction, we'll do the second method.